inquiry is often a bolt-on, but if you look in the syllabus, it's really worth as many marks as the ideas. It can be assessed in many different ways, but unless we've got a kind of strategy for how to embed it across the 5 years, it's quite likely that students won't be as competent with it as they need to be. So we're going to look at what exactly are the demands in the kinds of difficult questions that we showed you, and then we're going to work out what we need to do with the curriculum to prepare students for them. It's a design approach. Like engineers, we imagine what the solution's got to do, and then we work backwards and go, okay, so what does that mean for the curriculum, for assessment, for teaching? Often we don't think that way. We just sort of plan lessons individually, but the luxury of creating this 5-year plan has meant we can think at this sort of holistic level. And just to give you the goods right up front, these are the 2 basic principles that we're going to show you and how to implement them. So if you want to leave right now, you have got the main ideas, though you may not quite get how to use them yet. The first one is automatize, make fluent these inquiry skills. And the second one is actually not the knowledge, it's an ability, which we're going to call scientific thinking, and we're going to explain what that's all about. So that is really the agenda for this webinar. We often like to start with an exam question that's a challenging one because it makes us think more clearly, and it gets away from just looking at the specification, which is just the content. Here is what you've got to be able to do with the content. So if you've not read it, have a quick read now. What I want you to look for is, 1, what are the science ideas student needs? And 2, what kind of inquiry skills or thinking do you think is involved? So 1 minute. Let's have a few messages in the chat to identify some of the ideas and skills. We've got graph skills. I'm sure there must be more than that. So what else is needed here? Good, we've got interpreting. So we'll give the game away now. Transpiration, absolutely. So transpiration, photosynthesis, adaptations. There's multiple science ideas clearly involved in doing this question. So that makes it hard. And then, to make it harder still, we've got several inquiry skills, at least these. So you've got the patterns in the data, as you've already said. We've got an understanding that there are variables involved in a situation, and that temperature and rainfall are variables, and the transpiration rate, which is affected, is another variable. And then we think there's also skills involved in terms of hypothesizing. In other words, let's go back. You might look at the graph and you might go, okay, so I think what's going on is this. And then you've got to decide whether your hypothesis of what the explanation is actually fits the evidence on the graph. So you do have to understand the link between an idea and the evidence for it. So quite a lot of inquiry thinking, as well as lots of ideas. what's the result? Well, firstly, for many students, it would be cognitive overload. Too much to process. Too much, in other words, it's new to take in and figure out. And we know this phenomenon very well. And we know that there's a limited amount of working memory that everyone has. And if you fill it up too much, then students basically can't problem solve. And so what do we do about that? Well, the science suggests that the only way to reduce this bottleneck is to make a lot of the skills and ideas, but we're dealing with skills today, make them automatic, more like fluent skills, because when they're in long-term memory, our system doesn't need them to take up space in the working memory. That's just how our memory is. There's an infinite storage of long-term, but only a small working memory. So the more you can kind of make fluent and stored away, the more space you have for what's new. And obviously there are new aspects to the question, and you need to keep your working memory as free as possible for those. So key strategy here for inquiry, just as much as it is for facts and ideas, is to get those skills well learned. We're going to look at what that means for the curriculum shortly. There is a second challenge, which is probably harder to see. Though if you were kind of introspecting, that means looking at your own thinking while you were reviewing that question, you would realize that you have to keep kind of floating between an idea and a skill and some kind of metacognition of thinking, okay, so what do I know so far? And is that working? So you are kind of coordinating lots of things together, ideas, evidence, skills. And this coordination is what's known as scientific reasoning, which we're going to call scientific thinking, because reasoning sounds a little bit kind of overwhelming. It is thinking like a scientist. We can break it down, we can look at the skills and the ideas, but really what we're talking about is how to weave them together. You might know them all individually, but just being able to recite them doesn't mean you can actually put them together. So we think it's actually a different kind of ability. It's not enough to know the knowledge, you actually have to be able to think this way. But it's a little bit less common to think about this, so let's unpack it a bit. What do we mean by scientific thinking? And here is our big secret number 2, how to develop it by coaching students to think this way. If anyone's been familiar with the primary science curriculum, you might know that it says there are 5 types of inquiry, and students should have experience doing all of them: classifying, fair tests, patterns, observing, and researching. So when they come to secondary, those 5 types of inquiry kind of morph into the sorts of scientific thinking that we're talking about. I'll define these in a minute, but the names are classifying. Experimental is how fair tests sort of elaborate into the whole methodology of doing experimentation with variables and, valid, reliable data. Patterns morphs into things like quantitative relationships and statistical probability of certain things increasing other things. And then researching, which of course in primary means you don't actually have all the explanations yourself at that stage. By secondary, we're asking students to come up with explanations based on all the theory that they're being taught. So those are the 5 types of inquiry or types of thinking that are going on in science. Here is what we define them as. So classifying means categorizing, distinguishing one thing from another. Obviously, we're doing that all the time when we're looking at cells or elements. And that's the first stage in doing any science, is to kind of say, what is out there? What is it actually all about? But then scientists go to the next level and they go, okay, so I know what's there. What causes what? I want to understand these patterns. And of course, humans are all primed for figuring out cause and effect. So experimentation logically follows. And then, because you can't experiment on everything, sometimes you've got to look for patterns of what tends to go with what. And a lot of scientific work is about the correlations. But really the aim eventually is to come up with a mechanism to explain. And that is basically what the secondary science curriculum is all about, is developing these models, theories, ideas to describe and account for all the phenomenon that we see around us. And in some cases, we can go to the last stage, which is being quantitative and being mathematical. So I hope you can see that this is really another description of what is in the specification. And what I want to convince you is that every single idea in the specification, but particularly the main ideas, the key concepts that we're focusing on in Blueprint, each one of those can be linked to a particular way of scientific thinking. And I'll tell you what they are, and then I'll tell you why that matters in a moment. So theorizing, obviously the atomic model is a great example of developing a theory for the observations that Rutherford and others found. Experimental, most of scientific discoveries have been made this way, an example being radioactive decay. And then, of course, classifying, the periodic table, coming up with patterns. A more recent example is the statistical approach used to determine that smoking caused lung cancer. And quantifying, of course, the classic example being Newton's laws. So, in fact, you can make a link between every single idea and a way of scientific thinking. So here's the secret of why that matters. If you look at the specification and you look at the way ideas are described, here is transpiration, the example that we used in the question at the beginning. Look at the way it's described here. Doesn't it suggest to you this is all about experimental thinking? Because what that sentence is saying is explain the cause and effect relationships between variables, temperature, humidity, rate of transpiration. What students have to understand is how they link together. And the way they're going to do it is obviously going to be given situations, somebody's experiment or some phenomenon that someone was observing, and they're going to be looking at the data to draw conclusions and relate that to the variables. So the payoff really to think about the scientific thinking involved is that you've got an insight into the way that the examiners are likely to treat this idea. If transpiration is an experimental thinking idea, then the most natural way to test it is to come up with experimental situations like the one in that past paper and get students to put together the cause and effect. So when you know what to look for in the spec, these ways of thinking pop out at you. And once you know what those thinking styles are, you can see that they link quite nicely with the sort of inquiry skills that are in the knowledge of the specification. So in other words, if you're doing experimentation, obviously you're hypothesizing, you're investigating, you're interpreting. And if you are theorizing, you're using the process of modeling, and quantitative thinking involves a lot of mathematics. So what we think is that by taking this approach, you'll get students thinking in just the same way as the questions they'll be tested on, and B, it tells you, gives you a big clue as to what might be a good approach for how to teach the ideas so that students are already thinking in that way. A brief pause. Gemma, do we have any questions?
Nope, not at the moment.
Okay. So the next section, what we'll do is we'll take these two principles and we'll deal with them one by one. First, the inquiry skills, and then the scientific thinking. So I'll just set out what the skills look like in Blueprint, and then Gemma will show you what you can do with them. So how are we going to automatize inquiry skills as we discussed that we need to? There's kind of 4 parts in Blueprint. 1, we're going to define them. 2, we're going to make sure they all get taught early on, year 7 and 8. And 3, we're going to repeat them regularly across the whole 5 years. And finally, obviously we want students to become independent after 5 years. We're going to assume that you're going to use some kind of model like gradual release of responsibility, which means you do all the work at the beginning and gradually the students take over with less and less guidance needed. As they go through the 5 years, they should be able to do more of these skills themselves, which is what we want them to do so that they become fluent. So here is the list of skills. There's 27 of them actually linked to these areas: modeling, argument, investigating, interpreting. And as we said before, they're also linked to these ways of scientific thinking. So what we've done is we've embedded all of these skills in year 7 and 8. And the critical point is that you've got so many skills, the only way to be able to teach them and focus on them is to do them one at a time. We really think, because of the idea of cognitive overload, that it makes much more sense to focus on one for each particular idea. So here, potential energy, we've chosen the skill, review a hypothesis against evidence, because it fits very nicely into the way that you could teach that. So we could have chosen any skill. In fact, if you're doing an experiment in physics, you could have done variables, you could have done the quality of the data, you could look at patterns, but we chose this skill because we covered loads of the other skills in other units, and we wanted to find a good unit to cover this one. So in a sense, it's a jigsaw puzzle. We want to fit all the skills in and try and fit them as well as we can so that the activity naturally partners the skill. And that particular skill gets repeated in many different places. Again, there's only one skill which we kind of foreground for each scientific idea. You could choose lots of skills, but we've foregrounded them to make sure that each one gets its place and has enough opportunity to practice. So that's what Blueprint does. What we thought would help you is if we now focus on what can you do with the scheme that you already have to teach inquiry better. And I'll hand over to Gemma.
Okay. So I'm going to have a look at, first of all, a typical inquiry activity that you might find in a scheme of work. And we're going to have a look at, well, critique that. So we'll start off. This is what we see in many schemes. So inquiry skills are really only used in the occasional investigation style lesson, which are normally tagged on to the end of a topic. And they typically follow this kind of style. So students are giving an aim, then they make a prediction, then they follow a simple method, they think about the variables perhaps, then they collect their results in a table, then they analyse them, draw conclusions, and then they might do a bit of evaluation at the end. So can you think of any issues about teaching inquiry in this way? Just let you think for a couple of seconds. Okay, well, let's have a look. Firstly, and Tony's touched on this already, is cognitive overload. Rather than concentrating on one main skill, students are asked to use several with no real focus on building any kind of understanding on one main skill. So with no priority given to a skill, it's unlikely that students are then going to focus enough attention and thinking time to actually make any meaningful learning from that. And also, when inquiry skills are mainly taught in this investigation style lesson, you will find the same skills are being used again and again throughout the year, mainly the ones that I've got on that slide. So not much thought is put into thinking about what the whole range of inquiry skills that students need to develop and where is the best place in the curriculum to fit those and make sure they're all covered each year. So that's not really giving much time over to develop scientific thinking. And as Tony said before, it's a really important part of the curriculum that we can't overlook. Secondly, then, there's no real scientific thinking. There's no students not really getting the idea of why these skills are being used. So a good example here is identify variables. So students are given a method to follow and then they're asked to identify variables, but why do they need to do that? Surely you only need to do that if you are planning a method. So there's no real thinking process involved, no thinking behind the doing there. And also there's no context to connect that skill to. There's no mention of why scientists care about how friction differs with different materials. Why would they bother to investigate it? So isolating and focusing on a skill is good for explicit instruction when you're trying to teach the skill. But if you don't connect it back to a context, it's unlikely that students are going to be able to transfer that knowledge to a new situation. And that is the kind of questions that are coming up in exams. They're using familiar experimental techniques and familiar skills, but in unfamiliar situations. And basically, if we want students to think like scientists, then they're going to have to think like scientists and be given problems to solve using inquiry ideas. And I will come back to this later and I will show you what context we used in friction. And we used the same experiment, but we used it within a context. Okay, another issue is that skills are not being taught. If we want students to get better inquiry, they need to be taught those skills by modelling how to use them by an expert, the teacher, and then followed by guided practice. And finally, many schemes are missing places to assess those inquiry skills. And that is really important that they are, but it's difficult to assess inquiry skills. And so that's why in many schemes you don't find assessment just based on the skills. But we'll go back to assessment in our next webinar and learn more about that. Okay, is there any questions there? No? Okay, I'll go on then. We'll have a look at now how you can integrate inquiry into your schemes. So we've gone and have a look. We've had a quick look at the blueprint planners, and they've been designed to help you easily make changes in how you plan for inquiry. So I'm going to have a look at these 5 changes that you can make to your schemes. So the example I showed you earlier, there was that practical task from a lesson on friction. So let's have a look at part of the planner on friction from Blueprint. So the acquire goal, which is what you base the activity in the lesson around, is to choose a suitable material for an application by investigating what variables affect the frictional force between surfaces. So that is the same practical as I showed you before, and it's probably a similar one to what you already use. So converting this lesson so it only teaches a single inquiry skill, and so if it's in a new context, it's not going to be difficult at all. The planner then shows you the skill that we think is best linked, which is identify experimental limitations. So as Tony said, each key concept is linked to a foreground skill, which is the one that is going to be focused on, and it's the one that's going to be taught. Obviously, there's going to be lots of other skills if you do an experiment, but they're background skills. They're skills that aren't going to be taught, that students have already been taught before, and they can have a go at applying those. So we chose this identify experimental limitations because it's a skill not normally included a lot at Key Stage 3, but it's one that's built on at GCSE when they come to evaluating methods and suggested improvements. And we felt that it was a good link to this experiment because of the difficulty of making accurate measurements, of a force meter. If you've ever seen students do this experiment, it's really difficult for them to measure the force on the force meter that's needed to move the object. And also we've got a problem of controlling variables in here. So by linking each of these key concepts to a separate skill, we're giving plenty of opportunity to develop that scientific thinking. Second thing we can do is to add a need to know context. So that acquire goal says that students will be choosing a suitable material for an application. So we've given a hint to what kind of context you can use in this lesson. So you could get students to look at the best material for a rock climbing sole, or as we chose for our complete mastery lesson, a sole for a shoe that prevents people slipping over on wet floors. So this is providing a reason for the investigation. Students are going to find out what material could be used for that sole by doing an experiment. So we're giving them a reason why scientists do experiments like the one they're going to do. So we need to get somewhere in this lesson to teach the skill. We've come up with a recommended approach to teaching inquiry skills, and I will go through that in a minute. Also, we need to give students opportunities for practice, those inquiry skills. So these are two of the stages that we've got in our learning cycle, apply and analyse. And they've also got linked inquiry skills. Those skills might be the same as the ones in the acquire, or they might be different, giving students a chance to revisit skills. So here we've got the apply statement, we've got two of them. They're both linked to using modelling, so to practice using model friction as a model to explain things. And the analyse is about drawing a reasoned conclusion from observations. And students should be assessed at several stages throughout that learning cycle. So we've got the evaluate stage of acquire, so that's the exit tickets. And as part of the apply and analyse, as I've just said, and also questions in a summative assessment at the end of the concept or unit. Okay, any questions? Okay, so I'm going to go through quickly then our approach to how you can teach inquiry skills. So before we get there, just to say that Blueprint is a blended approach. So we're not tacking on experiments at the end of the topic. We're suggesting a way of teaching so students learn science ideas while they learn an inquiry skill, and they're practicing one of those styles of scientific thinking that Tony talked about earlier. So how can you teach inquiry efficiently? So this is an approach based on research on how you can teach an acquire lesson. So there's 4 stages. We've got the explain, that's where the teacher's going to clarify the need for the skill and then where it fits in. Then they're going to demonstrate the skill by using a worked example. Then the students are going to have a go, but they're going to be given support. And then they're going to have the independent practice. So they've mastered that skill. So that's called EDGE. So if we look at EDGE in action, this is an explore activity from our Year 8 acquire on variation. So again, it's a typical practical that you may do. students are going to be asked to work out how height depends on genes. So they're given these 3 different graphs, and they're told if it's one height gene, you're going to get this pattern. You're going to get some short and some tall, nothing in between. If it's many, you're going to get this bell curve shape. And if it's not anything correlated with genes, you're going to get a random pattern. So the first thing they do then is they measure everyone in the class's height, and they put that into a table. And then they're asked about, well, how can you show the data? How can you figure out what pattern that is? And they should realise that you can show the data as a bar chart, but it's going to take you a long time because you're going to have to show a bar for each of the students in the class. So that reveals a need to use a different type of chart. And that then is showing you the need for this new skill of drawing a histogram. So that's the explain stage. You're actually showing them where this new skill is needed. Then you're going to do the demonstrate stage. So at this stage, we've given students a sheet with lots of different monsters and their mass. So we're going away from the context of height. We're using something different to teach the skill. So the teacher then demonstrates the stages to draw a frequency table and a histogram from that data that they've got in front of them. So this is quite a complicated skill, so we're breaking it down in stages. So the teacher demonstrates the first stage, then the students, so this is the guide stage, they have a go at completing that stage. So this is a guided way of teaching the skill. So they will have a go, but it's very guided. And then when they've learned all of those stages, so now they're confident in how to draw a frequency table and a histogram, they go back to their height data and then they use that themselves. So in the empower stage, they're going to draw their own frequency table and histogram from that data, and then they can go back to the original question, which of those graphs does their data fit? So when should practical work be used? So we've got 2 places in Blueprint for practical work. The first, as I've already showed you, is part of an acquire. So the focus there is they're going to acquire the main science idea by using an experiment. So the example on the screen there is from the electric current key concept. So students will build circuits and draw conclusions to learn about what affects current. They're doing an experiment, but they're using it to learn a main idea. And the second place we put them in is some standalone practical lessons. So here there is no main science idea. The focus is very much on teaching the skill and practicing practical techniques, because that's another important thing they need to do. And of course, we've got the required practicals. So we've got all of the AQA combined science required practicals in Blueprints. There's 19 altogether, and they're in the planners as practical acquire lessons. So we don't want to spend time in those required practicals teaching a main idea. They're using it in a practical, and they're getting lots of opportunity to practice those techniques. Most of them are covered in a 9 to 11 key concept. We have a few in year 7 and 8, but we've also put in place opportunities to look at those again in 9 to 11, obviously, in case they forget them before the exam. Okay, that's all from me. Got any questions? Go on from Richard. Do you recommend students be made aware of EDGE? Does this ever cause confusion with the ease for the acquire stage? We haven't actually put it into the teaching PowerPoints that is the different stages of what they're doing. But I guess if you use it enough, the students will understand that those are the stages that you're going through to teach them a new skill, but I wouldn't call it EDGE, I don't think. Are there any other questions?
Only practical questions about the number of required practicals. If there are any more questions on what you've seen, please do start chatting, because I'm going to change the subject in a moment. We're going to broaden this into the scientific thinking. So please do ask Gemma any questions about how to change your scheme, how to add inquiry based on what you've seen. Obviously, we've given you one method. There are lots of different ways of teaching the inquiry. The main point being, Blueprint allows you to audit your current scheme, to see what's missing, and to suggest how to make sure every single skill gets taught early on. So one question I can see here, the planners are free, of course. We are promoting the use of the planners now. We have been supported by AQA and other organizations in their development, and so we were able to provide this 5-year plan so that anyone can use it. So I'm going to move on to looking at the scientific thinking problem. Remember, at the beginning we identified that one of the difficulties in using inquiry in an AO2 question is how to coordinate all the ideas and different skills together. And we've labeled this as scientific thinking. And we've defined 5 different kinds of thinking, that are used in all the ideas in the specification. So there's basically 2 ways the Blueprint helps you to coach students in scientific thinking. The first are the actual statements, how they're written. They actually describe the thinking style. And the second is the tasks that we've suggested, and we'll show you how they might look so that you're actually getting the students engaged in that thinking process rather than just telling them the outcome. Here is a planner for plant transport. Remember the question at the beginning. This is how we've described the main idea. You can see, if you read it, that this is about a set of cause and effect relationships. Have a quick read. What we tried to describe is how this system works. So why there is transpiration in the first place, and then what affects it, so that students can build up this model in their heads. By connecting all these variables together, we think they're more likely to actually remember that temperature, for instance, is important. In that past paper question, the examiners commented that almost nobody actually used temperature in their answer because they weren't really thinking about all these different variables. So that's the first way that Blueprint helps to describe thinking. The second is in the tasks that go along with the knowledge. Here is the task that we've suggested that you could use so the students actually learn about cell transport in this way of scientific thinking. So what they're actually doing is making predictions. So you might give them a setup, an experiment with a plant and investigating the water loss. But the important thing is that they get involved, and having got some basic knowledge, they can start making predictions about what they think would happen if you change some situation. And the more they do that, you can see they're likely to be prepared for the sort of question you saw at the beginning. There are lots of different ways, of course, you can teach this method. And I'm going to show you one of the more ambitious ones we put into our materials. A different context this time. This is oxidation and reduction, which comes from year 8. The scientific thinking idea here is really about theorizing, developing a model to explain the kinds of reactions that students would observe, try and get a deeper understanding of how particles recombine, and particular tendency for some substances to want to add oxygen and for others to want to get rid of it. I hope I'm not misstating the chemistry, Gemma, as I'm using my physics out of context. And so what could we do with this kind of idea to encourage scientific thinking, right? So notice that we're not going to go straight in there and say, here is a reaction and here's what's happening. This is oxidation and that's reduction. We don't want to do that because, in a sense, the teacher's done all the scientific thinking and the student's done zero. To us, that's missing a massive opportunity to get the students involved in just the sort of thinking that they're eventually going to have to do on their own in that past paper question that's waiting for them at the end of year 11. If they're not being prepared for it every time you teach the idea, how can we expect them to do it eventually on their own? So, as I said, this is an ambitious approach. Because it's about modeling and developing a theory, we thought it would make more sense that they're introduced to an actual situation and how an actual scientist came up with that theory. So here's the situation. We have a video. There's more to it than just the slide, but this gives you the idea. It's about air pollution and respiratory problems, particularly in the 50s in America. This was the impetus to develop, I wonder if you know what the invention was, to reduce the pollution from motor cars. Any ideas? Of course, it's the catalytic converter. That was the context we chose because it allows us to think about why we need this concept of oxidation and reduction. By putting that into a context, we're telling students that a scientific idea is there because it actually explains or solves a real life problem, just what the exam questions in AO2 do. So this is the context. And how do students get involved in scientific thinking? Well, in a sense, they're like an apprentice. This is the famous Eugene Houdry, who invented the catalytic converter. This is all true. He was trying to understand the processes involved when gases from cars created the pollution, and we want the students to kind of help him come up with his scientific idea, which then got turned into technology of the catalytic converter. If this seems a bit weird, I wonder if you've ever watched Horizon. The whole idea of Horizon is that you follow a scientist who's got a passion for solving some kind of problem, perhaps a disaster waiting to happen, or a medical cure, or fascination with something in the universe. This passionate scientist is trying to find out the answer. And that's the vehicle for the program to teach you a little bit about science through a kind of process of following the scientist at each step of their reasoning. As Horizon takes you through the story, they pose questions like this one here. How can we reduce air pollution? This is 50 years later. What actually happened to change the situation? Here are the objectives. This is all going to be about oxidation and hypothesizing. And the beginning of the lesson, I'll just stop here. It shows you the basic problem, which is all of these gases coming out of a car's exhaust. And here is the sort of link with Horizon. You see something, there's a question. How does this form? Now, we're not expecting the students to come up with all the answers, of course, but the point is that they're being asked to think. And whatever the ideas are, you can build on them and you can tell them what actually happens next. So this is the process we've used, that the children, the students in class are kind of playing along with the scientist's thinking until he gets to his hypothesis. And then to do the experiment, they can actually do the chemistry themselves, and they have much more meaning attached to why they're doing an experiment, because they can see that this idea is really important. It's going to solve a global problem, and it's obviously a lot more motivating to do that. But at the same time, they're learning how to think scientifically, because we've embedded these questions on every slide that are either getting them to think more about the idea or to think about the skill. And can you see that that's a sort of training process in scientific thinking? It's kind of coaching the students to think more like the expert, who, of course, is the teacher. So that is one approach, just to inspire you, in case you're sometimes thinking, how do we make this theoretical chemistry idea come alive? Well, there's usually a way, whether it's a modern example or a historical one, or some other kind of problem solving, engineering or decision making. There's always a way, I think, to make these ideas come alive, and it usually involves some kind of scientific thinking, which is going to be more like real life. So I hope what we've done is shown you the possibilities of bringing inquiry in, both in the skills and in this broader scientific thinking.